So hopefully it's going to be able to record your guys' voices as well. I'm not actually 100% sure. Can someone talk real quick and see if my audio goes hot? Ah, crap. That's not working. Okay, so I will. Maybe I should fiddle with this right now. So I'm using OBS, which is also handling the streaming out. Um, and I think it's eating the wrong desktop audio feed. Let's try. All right, can I get someone to talk again?
Hello again.
Okay, cool. That one showed up, so we should be better on that. All right, cool. Um, so, unless anybody has something specific they wanted to take a look at, I kind of wanted to look at a couple of the trickier problems that I assigned in that related rates packets. Especially that clock problem, which I think everyone sort of got through, but I think everybody struggled with enough that I would love to just kind of go over it again and make sure that everyone's up to date on it. So, if you have anything that you would much rather me do at this moment, speak now or hold your peace for at least a while I do this problem.
Sounds good to me. I was definitely confused by that one.
Okay, so
Is
base.
the screen?
Sorry, say that again.
I'm sorry. You keep seeing the screen like going black and then back to normal. Is that every computer?
Uh, I don't think that should be happening.
The
Is it?
stream is stable here.
Yeah.
Yeah, I'm not getting any problems.
Is
I'll
any
troubleshoot that on my.
Okay. Is anybody else getting problems with the stream?
Katie, it sounds like your internet might be spotty also because your voice is cutting in and out a bit.
That's exciting. Okay.
Yeah. All right. Well, let's go ahead and start with this clock problem, right? So I changed the numbers just a little bit, so it's not the exact same problem, but the idea is still sort of the same. What we have is we have a clock, and the clock is it has a certain time. It has an hour hand, but the hour hand sort of a red herring. We're only concerned about the distance between the second hand and the minute hand, right? And as we know and love, clocks have numbers on them. And fortunately for us, the places where the hands point are going to be um, nice radian values for us. Right? So there's our second hand, and there's our minute hand.
Good. My screen keeps going
Okay, cool. And
black.
what we're trying to do here is we're trying to find the actual rate of change of the distance between the second hand and the minute hand, right? So um, we need to find this distance here. Let's call that distance r, um, and let's call the angle here between the two hands. Let's call that theta. Okay. Things that we know from the problem, we know that the second hand is 9 inches long. And we know that the minute hand is 8 inches long, right? So we need some equation that relates the three sides of an arbitrary triangle to the angle of the unknown side. And lucky for us, that is exactly the law of cosines. In this situation, the law of cosines tells us that the law of cosines says that r squared, the unknown side here, is equal to a squared plus b squared, which are the two known sides, 8 squared plus 9 squared, minus 2 times a times b, which is 9 times 8 times cosine of the angle opposite the unknown side, which is cosine of theta. Okay. So this is our relation. So right now we have a couple of things that are unknown that we're probably going to need to actually know. We need to know r and theta, hopefully. Theta we're going to have to figure out by actually looking at the problem and sort of figuring that out by the angle measurements on the clock. And then r we can figure out by what theta is using this law of cosines, right? So for theta, we can sort of imagine our clock as being in standard position, right? Like we can imagine it living on an axis.
Look at this. It's like not spazzing now.
Say that again. It kind of sounds like everything on your end might be spazzing out, Katie.
You hear me?
Yeah, vaguely. You're cutting in and out a lot.
Well, I thought my microphone looks like. No, it says it's muted. Wait, can you hear me now?
I can't hear you now. I have no idea what is going on with your stuff. Does anybody have any questions about the setup of the problem so
I
far?
don't know how to.
No, it seems so far it makes sense.
Okay. So to figure out these angles here, we need to figure out sort of what degree, like what angle we have here between the x-axis and 2 o'clock. That's 1/3 of 90 degrees, since 12 o'clock is up at 90 degrees. So this portion of the angle would be pi over 6 radians. And then the down part here between the x-axis and 6 o'clock here, the 30 seconds, would be something like pi over 2 radians. And theta should be the sum of those two angles, which is pi over 2 plus pi over 6, which ends up being 2 pi over 3. Let's make that actually look like a radian. Does everyone agree with 2 pi over 3? All right. I don't hear any shouts of despair or anything like that, so we'll continue onwards. So now to find r, let's use the law of cosines. So I'm going to jump over to this calculator over here, and we're just going to plug in our output there. Right? So it's going to be 8 squared plus 9 squared minus 2 times 9 times 8 times cosine of 2 pi over 3. And that gives us r squared is 217. And then we'll take a square root of that whole thing. So that gives us r is equal to about 14.73. So at the time of this problem, like when we first start thinking about it and we're trying to figure out what the rates are, we have an angle between the two hands of 2 pi over 3 radians, and then we have a distance between the tips of the two hands of 14.73 inches. Okay. So next up, let's differentiate with respect to time. So we're going to take our equation, r squared equals 8 squared plus 9 squared plus 2 times 8 times 9 times cosine of theta. And we're going to apply an implicit derivative with respect to time. Right, so
Sorry, can we back
ddt.
up for a sec?
Yeah, sure.
I'm a little bit confused about how we found the theta. I mean, it looks like you added those two angles together when I feel like you should be subtracting one from the other.
So in this situation, we're adding the two angles together. If you look at the actual clock, right, you'll notice that the angle that we're looking for is the sum of the two angles, right? It's the pi over 6 angle is up here, and the pi over 2 angle is down here.
Oh, I see. Okay, you're seeing.
So that's why it should be
okay,
the sum of the two angles there.
Yeah, because it goes over 0.
Yeah,
basically.
yeah. There's a handful of different ways of thinking about this. A 4-hour difference on a clock should be 2 pi over 3 any way you slice it. Every hour is approximately pi over 6 radians.
Right.
So 4 hours should be 4 pi over 6. There's a lot of different ways of thinking through this. Most of them are sort of geometric and intuitive, and some of them are not very satisfying from an algorithmic approach. So I tried to do one that was a little bit algorithmic, but it still was kind of up in the air, right?
Yeah,
Good
no, that
question.
makes sense.
Okay, so let's go back to our differentiation, right? Luckily for us, this derivative is actually not too bad. Most of this stuff in here is constant, right? We've got constants here, here. This is a constant multiple, right? So when we take our derivative, we should just end up with 2r times dr dt. 2r is the derivative of r squared, and then the dr dt is from the implicit differentiation, right? The 8 squared and the 9 squared just disappear, and we just end up with negative 2 times 8 times 9 times sine of theta times d theta dt. So here, the derivative of cosine is negative sine of theta, so it flips the sign on it. The constants remain intact, and then we have to multiply in by d theta dt as our implicit part. So notice dr dt is what we want to find. So d theta dt is something that we have to figure this out. So d theta dt is another thing that we're going to have to sort of use our head about, right? We're going to have to look at the problem, and we're going to have to think about what this rate should be, okay? So let's go back up to our clock. We look at our clock here, right? How fast is the second hand moving per minute? So every minute, the second hand does a full revolution. Or in other words, it moves 2 pi radians. And every minute, the minute hand moves 1/60th of a revolution. In other words, that's pi over 30 radians. Our second hand is gaining on the minute hand. They're both moving the same direction, but clockwise. But the second hand is moving faster, and it's behind in the clockwise sense, so it's catching up. So the angle between them is negative. And in fact, we get that d theta dt should be pi over 30 minus pi. Sorry, minus 2 pi. Question?
How do you get that it's pi over 30 minus 2 pi?
Well, so there's two ways of thinking about this. You can either think of it as 2 pi minus pi over 30, but then it needs to be negative. Or it's sort of the leading thing speed minus the trailing thing speed. That should be the rate at which the two distances are changing, right? If you think about it in a car, right? If you're driving your car and there's a car ahead of you, the car ahead of you is going 20 miles an hour, you're going 50 miles an hour, the distance between you is changing at a rate of negative 30 miles per hour. It's their speed 20 minus your speed 50 to get negative 30.
Okay, I think I get it.
Regardless, we should end up with 59 negative 59 pi over 30. Let's go back down to our calculus. We know that R was equal to 14.73. We know that theta is equal to 2 pi over 3. And we know that d theta dt is equal to negative 59 pi over 30. So now we can plug in. We get 2 times 14.73 is equal to, this 2 times 8 times 9 is sort of driving me crazy. I wish I had simplified it earlier. It's 144. So that's negative 144 sine of 2 pi over 3 times negative 59 pi over 30. Oh, and drdt is still over here. At this point, we should be able to plug some stuff in. We can divide both sides by this denominator over here. We get dr over dt is equal to 144 times 59 pi over 30 times sine of 2 pi over 3, all divided by 2 times 14.73. And finally, we just need to plug this into our calculator here to get our answer, right? So that'll be here, 144 59 30 times sine of 2 pi divided by 3, all divided by 2 times 14.73. And that gives us our answer that drdt is a positive number? That seems wrong.
You dropped your negative. Or did you drop your negative? Yeah, I think you dropped your negative.
Yeah. Uh,
Because it was negative 144 sine 2 pi over 3. And yeah.
but then it was negative 59 pi over 30.
Oh, I see.
So the let me think about this for a second.
No, that makes sense because your second hand is up near the 2 and your minute hand is going straight down. So as time progresses, the minute hand is moving away from the second hand.
Yeah,
So
but the second hand is moving towards the minute hand.
the second hand every minute returns to that position.
Oh.
So it's not moving.
This should be an instantaneous rate of change, though. Like it should be exactly how quickly it is changing at this exact moment. So the fact that it's not like every minute we're taking a snapshot, right?
Okay.
This distance should be decreasing. And now I'm trying to think of what I did wrong to make it not decrease. So our law of cosines is correct, right? That looks fine. This looks fine. What the hell did I do? Huh.
Everything looked correct to me, to be honest.
Yeah, I don't see any mistakes that I made here. Oh, I know what it is. Here, for some reason I turned that negative to a positive. So it should be a negative, which then gets canceled by the positive, which means that we should have had positive here, which means we should have a negative in front of this stuff. So here on this step, when I wrote our law of cosines, I accidentally wrote a plus.
Okay. Yeah, I see that.
So there was no negative sign to cancel. So when we did our derivative, we should have, or sorry, there was a negative sign, but this should be negative here. Or sorry, it should be positive after we do our derivative, because it was negative before, which means that our result should be a negative 144 sine of 2 pi, sorry, positive 144 sine of 2 pi over theta times negative 59 pi over 30. So we should have a negative sign in front of the whole thing at the end, and we should get negative 26.16 inches per minute. So there's your answer. So at 2:30, 10, the distance between the minute hand and second hand is changing. Sorry, let's just say it's decreasing at 26.16 inches per minute. And that's our answer to the clock problem. Any questions about this specific problem? Of course. My headphones will occasionally just decide that I have decided to ask for something and then mute everything around them so it can inform me that it couldn't connect. Did you say something, Manu?
No, I said everything seems correct, so yeah.
All right.
So, would we have to redo this whole thing if we had, like, 5 seconds later when the second hand had moved some?
Technically, yes, because theoretically everything would have changed later on, right? So ideally, you're in a situation where your program, like if you're actually, so first off, nobody gives a crap about how fast the second hand is moving in relation to the minute hand on a clock. Like that's never a problem that you. It's okay. That's almost definitely a problem you're not actually going to have to deal with in a real world situation, right? But it is a nice playground for these ideas of related rates, I think. And technically, your solution only holds for the moment that you were first thinking about. You would have to change some variables in order to deal with it at another time. However, the framework of the problem still applies. It would still be the same implicit derivative here, right? This would not change. So you would still be be plugging different numbers into the same derivative for a different time on the clock, right? So when you guys were doing this in class, your derivative should have looked like this. It should have looked the same as my derivative. We just plugged in different things this time around.
Okay. Yeah, that makes sense. All right.
Okay. Um, if that's the case, I think I can knock out one more of these, unless anyone has any specific things they want to see. Does anyone have one of these problems that they specifically want to look at? They're the same problems from the packet I handed you guys last class. I'm leaning towards doing either the Pivnert one or the Trough of Waters. Trough of Water.
Where can I actually download this packet? 'Cause,
I probably
I
should have posted
haven't
that.
seen
Yeah. Here, tell you what. I will post it to D2L right now.
Yeah, thank you, because I assumed we probably went through something, but I couldn't find anything on detail, and I was like, oh no.
Yeah, I'm pretty bad about that. I need to be better about that. I will obviously be better about that because in order to give you guys handouts now, I actually have to post them. So, let's make a handouts tab. And with. Oh, that didn't work. Okay.
I mean, you don't have to do it now. Like, I'm fine with how we're going through these problems right now.
Well, if I don't do it now, I'm gonna forget it. So
Okay, okay.
let's try that one. All right, check D2L. It should be under course materials, under handouts.
And I'm questioning myself on is the rest of the semester is going to be online?
Tentatively, that's the plan right now. Unfortunately, so yeah, we are. It depends on how things go, but that's sort of the plan.
Wow. Well, it's kind of cool that I paid less and I'm getting online services.
Yeah. That's not what I wanted. There we go. All right. So this is problem number 6. It has a trough of waters that's 20 meters in length, and its ends are in the shape of an isosceles triangle. So let's go ahead and let's start a new page. So we've got a trough of water. It looks maybe something like this. I think I'm spending too much time thinking about my art. And not enough time thinking about the math here. But it is 20 meters in length, right? So the length of it is 20 meters. And then it is in the shape of an isosceles triangle whose width is 7 meters and height is 10 meters. So the height here is 10 meters. And the width here is 7 meters. We need some sort of relation for that relates the volume of this shape to the height of the water inside it. But we should just probably start with the volume of the shape. Okay, so the volume for any prism like this is going to be the area of the base times the length. This holds for cylinders as well. The volume of a cylinder is the area of the base, which is a circle, times the length of the object or the height of the object. It holds for square prisms, any shape like this where you have some geometric shape at one end, and it sort of just extends that shape outwards into a three-dimensional space like this. They're called prisms, and they all have this same formula. In this case, the area of our base, so our volume, is equal to the area of the base, which is 1/2 of the width times the height. And then we're going to multiply that by the length of the trowel. So we'll just call that L for now. Any questions about this formula? And of course, as soon as I ask, it decides that it needs to take over. I think it has to do with the word questions. Like, I think, so I have Surface headphones, and I think every time I ask questions, it thinks I'm asking for Cortana, which I'm never asking for that. But I can't figure out how to turn it off. It's fantastic.
That seems so frustrating.
They're fantastic headphones. I love them so much. It's just that specific thing is the most frustrating issue in the world. I hate it. Everything else is good. Anyways, any questions about our volume here?
Nope.
All right. So a note here. We want this to be based on the height of water. Because that's what we're given in the problem, right? When the water is 6 meters deep, what is the rate of at what rate is the depth of the water changing? And we're given a rate of volume, right? So we need some way to write the formula for this volume just in terms of that height. You'll notice here, specifically the length is constant. No matter what height the water is, the length of the tank will still be filled up with all 20 meters, right? So we can just write that as 20. And the width and the height are also related to each other. And we may be able to write the width of this tank in terms of the height of this tank. Let's take a look at this triangle in a little bit more depth. Let's look at a two-dimensional projection of it into the XY plane. So we'll take axes here. And then we kind of have our triangle. This is by no means to scale, by the way, right? And we know that this point here is at 3.5, 10. The height here is 10 meters, and the width is 7 meters, so half of it is 10 meters, right? So what if we take an arbitrary point H along this triangle, right? Along this line here. What are the coordinates of this point? Actually, let's just call it X for now. Actually, let's not call it X. Let's look at the point itself. What are the X and Y coordinates here? Well, this line segment that we've drawn is the line. So this is on the line that passes through 0, 0, and 3.5, 10. Right? What's the equation of that line? Well, using everyone's favorite, well, this one's actually pretty straightforward because it passes through 0, 0, so that we know the y-intercept will be 0. And the slope will be 10 over 3.5 or 20 over 7. So that means that y is equal to 20 over 7 times x. In other words, our y coordinate here will be 20 over 7 times the x. But our y coordinate is half of the width. And the x coordinate is the height. Wait, what? Hold on. That's wrong. The x coordinate is half of the width. And the y coordinate, the height. So that means that height is equal to x is equal to 1/2 w, which means that 2x, yeah. So our height is equal to 20 over 7 times 1/2 w. So the height is 10 over 7 w. This is a little bit of a roundabout way to getting to this relation, but it's one that works. You can also sort of use the same logic that you would have used for the conical problem. In that an isosceles triangle, if you take any point along it, its width and its height will be related by a common ratio. So probably a smarter way for me to have tackled this is to use similar triangles instead, right? If I have this similar triangle that lives inside this bigger triangle, then the ratio of the sides is still the same. So no matter what, if these two triangles are similar, then the length of this side will be 7/10 the length of. So the width and the height will always be related by the same constant, that the height is 10/7 the width. So we can go back to our equation now and rewrite it. Our volume was equal to 1/2 of the width times the height times 20. So our volume is actually equal to 1/2 7/10 height is equal to W. So of 7/10 H times H times 20. Any questions about how we got to here? Oh my goodness. Okay. This is something that I absolutely need to figure out and fix. I might need to get a new set of headphones.
Yeah, I'm still trying to. It's making sense. It's just slow for me to go through. So give me a sec.
Mm-hmm. So basically, what I was doing here, this scratch work up here, is me trying to figure out what the relation, what is the height, or sorry, what is the width in terms of the height? So essentially, because I knew I had to take my relation and I had to write it entirely in terms of volume, in terms of height, because I didn't want to have a bunch of different variables floating around. I wasn't going to know the rate of change of the width, or at least I didn't want to try and figure that out. So we wanted to set it up like this. While you guys are thinking about it for a second, I'm just going to take this volume, I'm going to collect some constants here, which I believe is going to give us that the volume is equal to the 2 and the 10 and the 20 should cancel. So it should just give us 7h squared. So now we can take an implicit derivative. With respect to time. So we're going to take d dt of this whole mess. In other words, that tells us that dv dt is equal to 7 times 2h times dh dt, or 14h dt. Going back to the problem, so from the problem, the volume is increasing at 2 cubic meters per second. Sorry, per minute. And the current height is 6 meters. In other words, dv dt is 2, and d and h is 6. DHD, of course, DHDT is what we want to find. We can plug in our known variables now. dv dt is 2. So that's 14 times 6 times dh dt. 14 times 6 is 84. So when we divide both sides by 84, we get that 1 over 42 is equal to dh dt. That is the depth of the tank is increasing at a rate of 1 over 42 meters per minute. Any questions? Yep, I definitely need to get a new set of headphones.
Yeah. Or you just have to ask for questions without using the questions word.
Okay. Any concerns?
Does it work when the rest of us say the word questions?
No, because it can't hear that. It only hears. So it's got microphones because they're noise canceling, and the microphones are listening, which is. Yeah, it's not great.
Any cues, maybe?
Yeah. Any concerns? Oh, nope. That did it too. Good
Maybe
grief.
it's just the tone of the question.
Yeah, maybe. All right. So, I think that about does what I wanted to look at today. I sort of mostly just wanted to do a couple problems, make sure that my streaming platform wasn't going to destroy itself, and make sure that everybody could get in and access the lectures and be able to hear them and communicate with them. Obviously, Katie is having some trouble with her microphone stuff, so I will reach out to her and we'll try to get that fixed up before things actually go in a meaningful way. I will after I'm done here, I'm going to go ahead and try to figure out how long it's going to take me to upload this 45-minute video to YouTube. We'll figure it out, and I'll get a recording posted as well. Um, so, does anybody have anything they want to ask or talk about, or any problems they were having throughout this?
I'm still working on understanding that when water is 6 meter deep, like how we finding a rate from that point. But honestly, looking through everything, it's starting to making sense, and I'm
So,
like slowly breaking everything down.
essentially what we're doing is we're taking that information about when the water is 6 meters deep, we're taking the given rate. Like it tells us that when the water is 6 minutes deep, it tells us that uh, water is being pumped into the tank at a rate of 2 meters per minute here, right? Or 2 cubic meters per minute. So we're using this rate to figure out how quickly the height is changing or the depth is changing. Right? I probably should have been a little bit more fastidious about setting up the problem and identifying the rates that I was looking for and the rates that I was given.
Yeah, I was just I know that in the previous we like previous number we broke down such thing where time is a certain constant, and here we just kind of just plug in the values. And
Mm-hmm.
yeah, I don't know, I feel like every case has a different approach with
They're a little bit different every single time. That's sort of the struggle with related rates in a lot of senses. Every single problem is just a tiny bit different. You have this global approach to tackling all of them, but that global approach is it's very generalized. So it doesn't work in every single situation exactly the same way. Like the first couple of problems we did, like the ships at sea and the ladder type problems, right? These sort of problems, they are relatively straightforward in that you're finding exactly here is my relation, here are the rates I need, and I'm just plugging it in. These ones where we have like the clock hands and you have to think about how quickly things are changing on a clock, and the ones where we have like the triangular shapes and stuff like that are definitely a little trickier for sure. So,
Okay, yeah, I feel like I'm lacking geometry right now as I look through everything what we went through.
yeah.
Understand that we found a derivative of volume, and for the height, we just kind of plugged in whatever have been filled up with, so we would have a certain volume, and from that volume, we just kind of approached whatever the space it would fill up and
Yeah.
basically.
Conveniently, we didn't actually have to figure out what the volume was of this trough, right? We didn't have to know how much water was actually in it to begin with, because when we took our derivative, the v just fell off entirely. Sometimes that volume will not fall off entirely. Sometimes you'll still have that sticking around, but that's generally why I don't try and solve for unknown things, like unknown quantities, before taking my derivative, just because there's a chance that I may not need to know all of the information that's available.
Yeah, yeah. And as just the last question, so it would be a different rate of change at a different volume, right? Or I mean,
Mm-hmm.
at
At
the
a different height.
different amount of water.
Yeah,
Yeah,
that's exactly what Sam was asking about earlier. The rate of change will change depending on how long you wait, right? If we waited 40 minutes, then the depth of the water would be at 7 meters instead of 6 meters. And then we would have to think about, okay, well, at this time, how much water will be in the tank, right? So,
in the future reference, are we going to have like a specific formula which would be kind of same, and we would just have to plug in different things, and the rate of change would have been, or I don't know. I guess I answered my own question.
yeah. My expectation, if we were doing this traditionally, my expectation would be that you would, in fact, know geometric formulae, right? So I would be expecting you to memorize the volume of a cone and that sort of stuff. But obviously, since we're going to be doing something a little bit alternative with regards to assessment in this unit, I don't exactly know what I plan to require you to know, or how much of this is even going to be um, traditional. I'm leaning towards doing open note test for this next thing, like open note, open resources
Okay,
sort of
okay.
thing. So
Alrighty, yeah. I'm definitely gonna catch up with geometry. I had some issues with trig and I catched
yep.
up. And Now it's geometry time.
Yes, of course. So if it's not one thing, it's the other. And of course, for all of you, if you have anything you want to talk to me about, then please let me know. I'm perfectly willing to sit down and chat with you either over voice or you can do private chats on Discord. You can also get a hold of me in the traditional methods, right? But if you have any questions, then please reach out to me. I am happy to help you out with any of that sort of stuff. So.
So back
Okay,
to
cool.
our.
Oh.
Sorry.
I was just saying, okay, good to know.
Yeah. Okay.
So back to our trough here.
Yep.
If we kind of expanding on the implicit versus explicit, if we figured out a statement of volume in terms of time explicitly, and then took the derivative of that, that would work for different like water heights and everything else, correct?
So you can theoretically do something like that, but we had this conversation last class as well. I am a little bit worried about that. The reason why we do this sort of process is to avoid the fact that things become extremely complicated when we're not dealing with the derivatives implicitly. When we're trying to do them all explicitly and writing everything as a function of time and then slamming all those functions of time into the formula, you end up with stuff that's really, really complex to deal with. In some sense, there is approaches to this sort of thing that let us do that. What you're sort of seeing is like you're sort of approaching the idea of vector valued functions and that sort of stuff. But yeah, I encourage you to try to handle this implicitly, not explicitly, just for the sake of not driving yourself crazy or making minor mistakes here and there.
Yeah, I'm not planning to actually do it, but theoretically, like if you were writing a program or something, that'd probably be how you want to go about it. Then it would work for like all the situations.
Well, this works for all the situations in that same way. It's just a matter of what you're programming in. If you were programming something to actually do this, then there's a decent chance that, yeah, you would probably be programming it with sort of explicit valued functions and then going from there.
Okay.
So, all right. Any last questions, concerns, anything like that before I let you guys go and try to figure out what to do with this inevitably enormous video file that I ended up with?
No, not at all. Thank you for your time.
I'm good. Have a good day.
Yeah, thank you.
Good news, guys. I fixed my issues. so-
Yay!
Yay!
Just in time.
All right. Yeah, because I was saying before, can anybody hear me? Can anybody hear me? And nobody said yes. I'm like, that's great because
That's not a good situation, yeah.
I don't want people to hear me when I'm muted.
Yes, that is. Well, so my microphone is actually it's an active microphone. It's powered, and what that means is that when I turn it off, you can still actually kind of hear me if I get really, really, really close to it. Like my microphone is off right now, which is scary. But hey, that's how life works, I guess.
Also, I feel like I should let you know your mic is kind of cutting out a little bit, like for a couple seconds every time you talk.
Okay, so is it? It might be because of the way I have to do this. I don't have a hand free to use a voice activation button or to use a push to talk button, so I'm just using voice activation. I will look into my noise gates and make sure that it's actually picking up everything. Yeah, see, it just did it there.
Yeah.
Yep.
Okay.
Yeah, it did it for me too.
I might just set it so that there's no actual gate and I'm just constantly transmitting just to make everybody upset. But hopefully everything is quiet enough around where I am that I can make that work. I'm looking into some voice mixing type stuff too, where I can run I can run a separate noise gate that's maybe a little bit more accurate, or even just background noise filtering stuff. So I'll look into that and I'll try to get that fixed before next class. Were there any other technical things that people noticed?